Welcome to Theory of Computation. Today I am going to give an in-depth concepts of push-down automata. Push-down automata is an extension of finite automata which contains stack, set of states and input symbols in it. So at a time a finite state control is used to refer the alphabet symbols which will be stored in a string format in input tape, and also it will point to the topmost value on stack. Based upon these two symbols with the current state, either the push-down automata will go to the new state or it will be stayed in the same state. This will be repeated until all the input symbols in an input tape is read by the finite state control. So this is namely moves on PDA. So it is written with the transition function. So the transition function of a push-down automata contains 3 input parameters and the output value is stored in 2 values. The first parameter of input is a state, that is a current state. Second parameter is an input symbol which is stored in an input tape. Third is a topmost value on stack. So based upon the tape symbol and also the stack value, the current state Q will go to either P1 state or P2 state with the operation. So the second parameter of the output value depends upon the operations on stack. So if a stack is used to implement push operation, then we should represent 2 symbols in a output parameter of second value. Otherwise, if you are doing a stop push operation, only one symbol is stored as a second parameter value, and that symbol is an alphabet symbol or a topmost value on stack. Then if you want to implement pop operation, we should use epsilon as the second output parameter value. So this will be denoted like this. And types of PDA, 2 types are available, deterministic PDA and non-deterministic PDA. So how can we identify these differences means, for a transition function tilde contains only one output value, then that is called as deterministic PDA. But here in the slide, P1, P2, Pn are 3 different states are available. So at one transition function, there may be the possibility of more than one output state, means this type of PDA is called as a non-deterministic PDA. So like a finite automata, the default PDA is denoted only a deterministic PDA. And instantaneous description means if you want to check whether the string is accepted by the push-down automata, we should use that notations as a second parameter value in a push-down automata, and we should check whether the output state is reached or not. This sequential formation of step-by-step action is called as an instantaneous description. So here let M is a PDA which contains a 7-tuple representation. Q with a set of states, sigma is an alphabet symbol, tau is a function on stack, tilde is a transition function value, Q0 is an initial state, Z0 is the initial stack symbol value, and F is denoted for final state. And if the input string is AW, I want to check whether AW is satisfied by the push-down automata M. So this is Q. Q is the current state, and I want to check AW input string is accepted by this PDA M. Then now the stack contains topmost 2 values are Z alpha. So I want to check the notation. So currently the first state is Q, and the first input symbol that should be checked by the finite state control is A. The topmost value is Z. So Q, A, Z. if it gives an output as P and beta, we should write like this. That is, this is the next level of transcription. So instead of Q state, I changed it as P state. Then A is already read by the finite state control. So the next immediate symbol on tape is W. So I only write that W in the next step. Then instead of Z, I want to use beta. So here I am using beta. So Z is replaced by beta. The remaining symbol is alpha. So this is the next instruction, next step. Like this, it will be continued until that final state is reached by the push run automata. So this is called as instantaneous description. And the language of PDA means a PDA can be accepted by a correct input and it will go to an accepting state. So we can able to identify the language acceptance in two ways. If a final state is reached, that will also called as an acceptance of PDA. So we can stop the performance or a transition. Suppose if the stack is empty, that time also we should stop the process and we should check whether any further input symbols are available in an input tape or not. So like this only the language acceptance will be denoted. So this is the generalized definition of acceptance. So from empty stack to final state. So how can we check it? Let n of Pn, where Pn is the PDA which contains a 7-tuple representation, and the PDA if goes to final state Pf, then this is the final state notation. Empty stack means that time if you want to go to an acceptance state, either you should go to a final state, otherwise that stack should contain empty values only. That means the initial Z0 value only available as a topmost value on stack. That time also we can stop the procedure. So this is the fundamental steps are two different way of accepting a PDA. And equivalence, this is the problematic portion we are going to discuss here. That means the conversion of a context-free language to push-run automata. So how can we check it out? So there are a four-step procedure for implementing conversion of CFL to PDA. So in which they will give a context-free language and we want to construct a push-run automata from it. First step, if any language is given, first we should write a set of strings for that correct particular language. That means a language should contain correct strings within a set. So for that correct set of strings, we should draw a transition diagram. So I already told that push-run automata is an extension of finite automata. So the transition diagram is nothing but we should draw a non-deterministic finite automata for a given language. So in first unit, I already covered the conversion of a language to NFA and also the language to DFA. So you please refer those videos for the transition diagram of CFL. Then we should write the procedure for implementing that particular portion. The procedure means in which state we should implement operations. So I already told that there are three different operations can be performed on stack. One is push operation, and second one is stop operation, and third one is pop operation. So depending upon that we should write the procedure, and based upon the transition diagram and our procedure we try to write the transition function. So that is the construction portion. So the third step is an important point. We should validate that particular transition function notations with the correct input string. So if you give a correct input string for this push-run automata, it should go to accept state. And if you give a wrong input, it will go to reject state. So we should verify these concepts, and we'll discuss this problems in next class. Thank you.